Okay, so in the last couple of videos, we figured out how to set up an iterated integral in polar coordinates. We're actually not going to go through the process of creating the Riemann sum, but we needed to see that when we integrate in polar coordinates, if I'm integrating, again, f of xy dA, that's going to become the integral over appropriate limits of f of r cosine theta, r sine theta, r dr d theta. Okay, so that our dA has this extra factor. It's not just the change in r times the change in theta, it's r times that. And so when we're integrating, that's going to affect our integrand. Okay, so I want to just do that with this particular problem. So we're asked to find the volume that's enclosed by these two surfaces. So I'm just going to draw a sketch. I recognize that that's just my standard paraboloid that opens up. There's my z equals x squared plus y squared. This is also a paraboloid, but it's been flipped over because I'm subtracting the x squared and the y squared, and it's also been translated up 4. So its vertex would be at a height of 4, and it would be opening down. So we're talking about sort of an egg-shaped situation right here. Okay. So I know that if I'm integrating to find volume, I'm going to integrate over some region, and it's just going to be top minus bottom dA. But I'm going to need to figure out what that region actually is. Well, if I take a look here, I can sort of see that the bottom surface and the top surface meet at some point. It looks like they meet in a circle. We'll see if that's actually true. But where the floor and the ceiling meet, that defines this boundary curve. I'm going to project that onto the xy plane and then fill in that disk that's enclosed by that. Turns out that's going to be my D. That's now the common domain for the floor and the ceiling. Okay. The floor being the paraboloid that opens up, and the ceiling being the paraboloid that opens down. It's always the case that if you have a region where the top surface and the bottom surface meet, you can find that curve where they intersect, which may or may not actually lie in a plane. Drop that curve onto the xy plane, fill it in. That's the common domain for the floor and the ceiling of your region. So let's figure out what that is. That's going to be where the floor meets the ceiling. So I'm going to set those z values equal to each other. So x squared plus y squared, that's the z value on the bottom surface, has to equal 4 minus x squared minus y squared. That's the z value on the top surface. Doing a little bit of algebra, 2x squared plus 2y squared equals 4. X squared plus y squared equals 2. Looks like this circle is just a circle of radius root 2, which means that our disk, our region D, is actually a disk. It's just a disk of radius root 2, which is fairly nice. Okay. So that's the region over which we're going to be integrating. So we want to see if we can now set up our integral. Let me clear some space here. Let's see. I kind of want to keep that general setup there for the time being. So if I'm integrating over a disk, I want to describe my limits of integration in terms of r and theta. Okay. Well, if I'm integrating over the whole disk, I'm thinking theta is going from 0 to 2 pi. Okay. And then for each fixed theta value, this is just a constant theta ray, and I can see that r is going from 0 to the radius of that disk, so we're going to have from 0 to root 2 for our r values. Okay. Anytime you're integrating over a disk centered at the origin in polar coordinates, you will have constant limits of integration for both r and theta. Okay. That's kind of nice. So in rectangular coordinates, if I had this, I'd know I was working over a rectangle. In polar coordinates, if I see constant limits of integration for everything, I know I'm integrating over a disk or a part of a disk. Okay. But this trick of drawing in a constant theta ray to then see where do I start being in the region? Oh, I'm already there at r equals 0, and then I end at root 2. That can be a useful trick in general for figuring out our limits of integration. Okay. So now let's see, we're going to have top minus bottom. We determined that this was the top function, and I just want to write this now in polar coordinates. So subtracting x squared and y squared is just subtracting r squared. So this is 4 minus r squared, that's the top, minus the bottom, well, x squared plus y squared is just r squared, so minus r squared. And then dA is r dr d theta. I am always going to set up my polar integrals dr followed by d theta. That's because we've got to keep with the rule that we have functions inside and numbers outside. I'm sometimes going to have r as a function of theta. Theta is always going to be constant. Now, in this particular case, because I have constant limits of integration for both, if I wanted to, I could certainly Fubiniize and integrate with respect to theta first. I don't see any advantage for doing that, but there's definitely advantage to being in the habit of doing dr then d theta, because often r is going to be a function of theta. Okay. So I'm just going to multiply this out. Integral from 0 to 2 pi, integral from 0 to root 2. This becomes 4 minus 2r squared times another r. So it becomes 4r minus 2r cubed dr d theta. That r from the dA becomes part of the integrand. Now in this particular problem, if I left out that r, I still have a function that I could integrate. In a lot of problems, if you leave out that r, you are really screwing yourself over because you're going to have an integral that you just can't do. So it's very important in the setup that we always, always, always work with that. Okay, so let's actually evaluate this thing. I think that's going to be enough room. Okay, so I'm just going to come up here. Oh my goodness. Okay, so we'll have the integral from 0 to 2 pi d theta. That's our shell. We're doing the inside integral. Integrating 4r, I'm going to get 4r squared over 2, or just 2r squared, minus 2r to the 4th over 4, which will reduce to r to the 4th over 2. And all of that is evaluated between 0 and root 2. And then we still have to integrate that d theta. So that's the integral from 0 to 2 pi of what I get when I plug in root 2 minus what I get when I plug in 0, d theta. When I plug in root 2 squared is 2 times 2 is 4, minus root 2 to the 4th is going to be 4 divided by 2, which is just 2. I can do math. Okay, and when I plug in 0, I just get 0. All right, I can do math. 4 minus 2 is usually 2. So I've got the integral from 0 to 2 pi of 2 d theta. Since I'm just integrating a constant, I get that constant times the length of this interval, which is 2 pi, and so I get 4 pi. I'm very happy, by the way, that that is a positive number because we were finding volume. If we were finding signed volume, it's allowed to be negative. It wasn't signed volume, it was volume. And so I'm glad that we got a positive number. Yay!